This lecture is on buffers and introduction. A buffer solution consists of 1. A weak acid and a conjugate base, or a weak base and a conjugate acid, and 2. In the process, resist pH change by the addition of acid or base. This figure shows a buffer solution and its effect after adding acid or base in terms of the concentrations of CH3COH and CH3COO-. Here is a sample problem for you to try. What is the pH of the solution made by adding 0.500 mole of acetic acid and 0.500 mole of sodium acetate to enough water to make 1 liter solution? Ka equals 1.8 times 10 to the minus 5. After setting up the Rice table showing the equilibrium expression and reaction of both, and given Ka equals 1.8 times 10 minus 5, in solving for x, it equals 1.8 times 10 to the minus 5. The pH equals 4.74. Now, let's look at how a buffer works. Implementation of observing how a buffer works can be done by explaining it with the Chantier's principle with A weak acid in equilibrium, and B, a weak base in equilibrium. Here is a generic equilibrium system where aqueous HA and liquid H2O forms aqueous A- and aqueous H3O+. Weak acid molecules will react with additional base to neutralize it and produce more conjugate base. The reaction is HA plus OH- forms H2O plus A-. Conjugate base molecules will react with additional acid to neutralize it and produce more of the weak acid. The reaction is A- plus H3O+ forms H2O plus HA. In summary, buffers have these key characteristics. 1. Buffers resist pH change. 2. A buffer contains a large amount of either A weak acid with its conjugate base, or B, a weak base with its conjugate acid. 3. Acids neutralizes added base. 4. Bases neutralizes added acid. Here is a practice problem for you to try. Suppose you have a mixture of HF, Na+, F- and H2O. Which species will react with OH-? Which species will react with H3O+? The answer to the top question is HF. The reaction is aqueous HF plus OH- forms liquid H2O plus aqueous F-. The answer to the bottom question is F-. The reaction is aqueous H3O plus combines with F- forming liquid H2O and aqueous HF. Here's another practice problem for you to try. Suppose you have 50 ml of 0.100 molar solution of substance 1 and 25 ml of 0.100 molar solution of substance 2. Which of the following mixtures will result in a buffer solution? A, HF and NaF, B, HF and HCl, C, HF and KOH, D, NH3 and NaOH, E, CH3NH2 and CH3NH3 plus Cl-, F, CH3NH2 and HCl. The answers are A, C, E, and F. Not B because it is combining 2 acids, not D because it's combining 2 bases. Buffers are most effective when the acid-base ratio is 1:1. Buffers can be effective when the acid-base ratio between acid and base is between 0.1 to 10. Therefore, buffer range is pK plus or minus 1. Buffer capacity is the quantity of acid or base that the buffer solution can absorb while maintaining the pH within the range. Buffers are most effective when the acid and base concentrations are high. Buffer capacity depends on the amount of acid and base present. Case 1, same volume, different concentrations. If two solutions have the same volume, the solution with the higher concentration will have the larger buffer capacity. For example, 500 ml of 0.1 m HA with 0.1 m A- will have a larger buffer capacity than 500 ml of 0.01 m HA with 0.01 m A-. Case 2, same concentration, different volumes. If two solutions have the same concentration, the solution with the larger volume will have the larger buffer capacity. For example, a solution of 500 ml of 0.1 m HA with 0.1 m A- will have a larger buffer capacity than a 200 ml solution of 0.1 m HA with 0.1 m A-. Here is a practice problem for you to try. Suppose you have a buffer solution containing a combination of HNO2 and NaNO2. Which combination has the largest buffer capacity? A. 200 ml of 0.01 m HNO2 and 200 ml of 0.01 m NaNO2. B. 500 ml of 0.1 m HNO2 and 500 ml of 0.1 m NaNO2. C. 200 ml of 0.1 m HNO2 and 200 ml of 0.01 m NaNO2. D. 500 ml of 0.01 m HNO2 and 500 ml of 0.01 m NaNO2. The answer is B. In looking at the Henderson-Hasselbalch equation, since for a weak acid, Ka equals concentration of H plus times A minus over the concentration of HA, the final equation is pH equals pKa plus log of the ratio of concentrations of A minus over HA. Note concentration ratios of A minus over HA equals concentration ratios of base over acid. Note this equation is applicable to buffer solutions. Here's another sample problem for you to try. A buffer is made by mixing 0.300 moles of HC7H5O2 and 0.300 moles of NaC7H5O2 to enough water to make 1 liter of solution. Calculate the pH after 0.030 moles of NaOH is added. Ka equals 6.5 times 10 to the minus 5 for benzoic acid. Here is the Rice table showing the effect of the addition of base NaOH. In the end, in units of millimoles, are benzoic acid with 0.270 millimoles and benzoate ion with 0.330 millimoles. Since this is a buffer, the volume for each concentration is the same, so the ratio of molarity can be written as moles divided by volume. When the ratio is between 0.1 and 10, one can express the ratio in terms of moles. The final pH of this buffer solution is 4.29. This equation can also provide some insight as to what percent of the acid has been dissociated depending on the difference between the desired pH and pK of the weak acid. Let's look at an example involving acetic acid and sodium acetate. Aqueous acetic acid plus liquid water forming acetate ion and hydronium ion. Imagine you make an acetic acid solution where one molecule has a pH that is 2.00 pH units above the pK of acetic acid. K equals 1.8 times 10 to the minus 5, and pK equals 4.74. pH equals pK plus 2.00 equals 6.74. Since the pH equals pK plus 2.00, then the log of base over acid concentration ratio equals 2.00 and base over acid concentration equals 100, which also equals 100 over 1. This means that 100 of every 101 molecules of acetic acid are dissociated, with the percent dissociated of 99%. This illustrates the other relationships between the difference of pH and pK. As evident, here as the ratio between base over acid decreases, the amount of the original acid molecule dissociates to its conjugate base, as seen by its percent dissociated decrease. The general idea is to be able to select an appropriate acid whose pK is closest to the desired pH and adjust the base over acid concentration ratio to the value in accordance to the Henderson-Hasselbalch equation. Let's look at an example. Here is another sample problem for you to try. Suppose you want to prepare a pH equals 4.00 buffer solution and you were given the following acids along with their sodium salts available for use. A, HC2H3O2 or acetic acid with a pK equals 4.74. B, HNO2 or nitrous acid with a pK equals 3.34. C, HC7H5O2 or benzoic acid with a pK equals 4.20. D, HCOH or formic acid with a pK equals 3.74. Which acid and salt combination would you use and why? Support your answer with calculations and explanations. Here are all four acids in use with the Henderson-Hasselbalch equation. Now, after subtracting pK from pH, the final answer is benzoic acid and sodium benzoate because the base to acid ratio is most closest to 1 and is best for preparing the desired pH solution.